Welcome to our Algebra series. Today we are going to explore a fundamental and powerful concept called the rank of a matrix. By the end of this lesson, you will understand how to look at a grid of numbers and determine exactly how much unique information it actually holds. Let us dive in. To understand what rank is, imagine you are managing a construction team of 3 workers. Worker A lays bricks and worker B mixes cement. But worker C just watches worker A and copies exactly what he does. Even though you are paying 3 people, you only have 2 independent workers doing unique jobs. In linear algebra, a matrix is exactly like this team. Each row or column is a worker. Sometimes a row just copies or combines other rows, bringing no new mathematical information. The rank tells us how many truly unique, independent rows we actually have. Now that we have our analogy, let us look at the formal math. The formal definition of rank relies on a concept called being linearly independent. A set of rows is linearly independent if none of them can be created by simply adding or multiplying the other rows by a number. Every independent row brings completely new, irreplaceable information. The rank of a matrix is defined as the maximum number of these linearly independent rows or columns. Interestingly, whether you count the independent rows or the independent columns, that maximum number is always exactly the same. Before we calculate anything, let us see this visually. Here we have a 3-dimensional coordinate system with x, y, and z axes. Notice the flat, shaded 2-dimensional plane slicing through it. We have 3 vectors labeled v1, v2, and v3, all lying flat on this single plane. Because all 3 vectors are trapped on a 2-dimensional surface, the third vector does not give us any new direction. It is just a combination of the first 2. So even though we have 3 vectors, the rank or the true dimension of the space they span is only 2. So how do we actually find this rank? We cannot always just look at a matrix and guess which rows are redundant. Instead, we use a systematic method called row reduction to transform the matrix into what is called echelon form. Echelon form is a staircase-like arrangement of numbers. By subtracting multiples of one row from another, we force the hidden redundant rows to reveal themselves as rows of pure zeros. Once the matrix is in this staircase shape, we simply count the number of rows that are not completely zero. That count is our rank. This brings us to an important mathematical rule about the absolute limits of rank. The formula on screen states that the rank of a matrix A can never be larger than its smallest dimension. Here, the Greek letter rho represents the rank of the matrix. The letter m stands for the total number of rows and n stands for the total number of columns. The function min simply picks the smaller of those two numbers. For example, if you have a matrix with 3 rows and 5 columns, the maximum possible rank is 3. You are always bottlenecked by the smaller dimension. Now that we know the maximum limit, what happens when a matrix actually reaches it? When a matrix hits its maximum possible rank, we call it a full rank matrix. For a square matrix, meaning it has the exact same number of rows and columns, being full rank is a very special and powerful property. It means absolutely no information is redundant. Every single row and column is linearly independent. This property is directly tied to another major concept called the determinant, which measures if a matrix squishes space flat and loses information. Let us look at the mathematical relationship for full rank square matrices. This chain of symbols tells a beautiful story. The first part says the rank of A equals n, meaning it has full rank. The double arrows mean if and only if, showing these statements are perfectly equivalent. The next part says the determinant of A is not 0, meaning no information is lost. Finally, the last part states that the inverse of matrix A exists. In plain English, if a square matrix has no redundant rows, its determinant is not 0 and we can perfectly reverse its effects. Before we move on, let us see this with a concrete example. We want to find the rank of a specific 3 by 3 square matrix, which we will call A. Our goal is to perform row operations to see if any row turns into all zeros. We start by using the first row to create zeros in the column below it. The first number in the third row is a 1. If we subtract the entire first row from the third row, that 1 becomes a 0. We apply this subtraction to every number in the third row. Continuing with our row operations, look closely at the new matrix we just created. Notice that the second row and the newly formed third row are exactly identical. Both read 0, 1, 4. This is a massive clue that we have redundant information. To prove it mathematically, we perform another row operation. We will replace the third row with the third row minus the second row. Since they are identical, subtracting them will leave absolutely nothing behind. Let us look at the final result of that subtraction. The matrix is now in perfect echelon form and the entire third row has become zeros. This proves it was just a combination of the first two rows all along. To find the rank, we simply count the remaining rows that have at least one non-zero number in them. There are exactly two non-zero rows left. Therefore, the rank of this matrix is 2. Even though it started with 3 rows, it only contained 2 rows worth of unique information. Now let us tackle a rectangular matrix, which has a different number of rows and columns. Here is matrix B with 3 rows and 4 columns. According to our earlier rule, the maximum possible rank is 3, the smaller dimension. Before doing complex math, we inspect the rows. Look at the first and second rows. If you multiply every number in the first row by 2, you get exactly the second row. This means the second row is completely redundant. We eliminate it by replacing row 2 with row 2 minus 2 times row 1. Following that subtraction, our second row is now entirely zeros. However, to put this into proper staircase echelon form, all rows of zeros must be at the very bottom. So we need to swap the second row, which is all zeros, with the third row, which still contains numbers. Swapping rows does not change the underlying amount of information in the matrix, so it does not change the rank at all. Let us perform that swap now. Here is our final arranged matrix. It is now perfectly in echelon form. We count the rows that are not entirely made of zeros. The first row has numbers and the new second row has numbers. The third row is completely empty. Because there are exactly 2 non-zero rows, the rank of matrix B is 2. This confirms that out of the 3 original rows, only 2 were linearly independent. You might be wondering why we care about finding redundant rows. Understanding the rank of a matrix is incredibly important in the real world. When engineers design a bridge, they use matrices to represent physical forces. If the rank is lower than the number of physical joints, their equations lack the unique information needed to guarantee the bridge is stable. In computer science, rank tells a computer exactly how much memory it needs to store a massive dataset, allowing for heavy data compression. Without rank, we would waste massive computing power on useless information. Let us wrap up what we have learned today. First, the rank of a matrix measures the number of truly unique, linearly independent rows or columns. It represents the true information content. Second, we find the rank by using row reduction to create an echelon form, and then we simply count the non-zero rows. Finally, a full rank square matrix has no redundant data, meaning its determinant is non-zero and it can be inverted. You now have a solid understanding of matrix rank. Great job!